You will love these properties because, in essence, they are shortcuts. That means that we have some easier ways to do them than what we were doing yesterday, where we were having to use the definition of the definite integral. All right, so the first one, they tell me that if you have the integration from b to a of f of x dx, that will be equal to the exact opposite of the integration from a to b of f of x dx. Remember that integration is always going to be a definite integral anyway, is always going to be an exact value. And so if my answer for the first integral was a positive 2, the answer for the second integral would be a negative 2. And the reasoning behind that is, like let's say you're working on the interval from 0 to 6. If you do b minus a, you get 6, but if you do a minus b, you get negative 6. So it makes sense then why that would be the opposite, depending on the order that we're in. The second property that they give me says the integration from a to a of f of x dx is equal to 0. The idea there is, okay, if you start at a and you stop at a, how much area did you cover? 0. So that's why the area under that curve would be 0. All right, the next one says if you integrate a constant, your answer will be the constant times b minus a. Now, if you think about that, come back up to this drawing that we had up here. Let's say that we were integrating, it was the integration from 0 to 6 of 2. Okay, so if I graph 2, it's of course a straight line. So when I go to find my base is just going to be b minus a. So that's the base. The height is just going to be the y value. The y value is my constant, right? So literally, if this was y equals 2, that would just make a rectangle that, this dimension would be 6 and this dimension would be 2. So I would do b minus a to get the base of 6, and I would do the constant c, which was 2, to get the height of 2, and I would have my area of 12. So you can see why that makes sense. All right, the next one they give me is the integration of two things that are being added, and they tell me that we can break that into two separate integrals that are being added. That should be logical to us since we had that formula for summation that was the same thing. We had the summation of two things that were being added. We could break into two separate summations. Remember that a definite integral by definition is just a summation, right? So that makes sense. Notice the notation here that every time we have an integral sign, it's always going to have a dx with it. So we had the integral with the dx, and then we had another integral over here, so we needed another dx over here. All right, next one they give me is the integration of a constant times a function. And they tell me that you can pull that constant out in front and get it out of the way and just work on the integration of the function and then multiply through by that constant at the end. Again, we had a summation formula just like that, and summations and definite integrals are the same thing, so we understand why that's there. And then the last one, we've got the summation of f of x minus g of x. We can break that into two separate summations, so the summation of f of x minus the summation of g of x. All right, so look at example 6. Example 6 on 332, it says use the properties of integrals to evaluate the summation, or the area under the curve from 0 to 1 of 4 plus 3x squared dx. All right, to begin with, I'm going to break that apart into two separate summations so it's a little less complicated and a little less challenging to deal with. Be sure, though, that with your notation, you keep the integral sign and the dx together, integral sign and the dx together. So if I have two integrals, I have two dx's. Okay, for this first one, we're going to have the integration of a constant. What did we say we would do if we were integrating a constant?
Just constant times c.
Yeah, the constant times b minus a. So we're going to take our constant 4 and multiply it times our b value minus our a value. So the area under that curve would be 4. Now, in my opinion, the book kind of cheats here. We could evaluate this definite integral, but we would have to go back and do it by the method we were using last night, right? Where we would go through and write it as a summation and find the change in x and find x sub I and use the definition and take the limit. We could do that. Instead, they say We worked this problem back in section 5.1 in example number 2, and we got 1/3, so we're just going to cheat and pull that answer from 2 sections ago and throw it in here. So, okay, we've already worked that one before, so fine, we'll just pull that answer and use it, but we could do it by the method we learned yesterday as well. Okay, so we can go through then and say that first piece we found was 4. For the second piece, we pulled our constant out in front and got it out of our way, and then we used the problem that we had already worked in example 2.5.1 that we had gotten an answer of 1/3 for. And so we can say 4 plus 1 is going to give us 5. All right, then some more properties. On the bottom of page 322, property number 5. Some of you are still writing, so I'll hang on a sec. Okay, so property number 5 says the summation from a to c of f of x dx plus the summation from c to b of f of x dx would be equal to the summation from a to b of f of x dx, right? Here's the idea. If you're finding the definite integral, the area under the curve from a to c, and then you add to that the definite integral, or the area under the curve from c to b, wouldn't that have to be the same thing then as the area under the curve from the starting point A to the stopping point B? Well, that's what we've got right here. So that's all this says. If you go from A to C and then you add to that from C to B, that'll be the same thing as if you started at A and stopped at B. So here's an example of that. Example 7 says if you're integrating the function from 0 to 10, and that value is 17, and you're integrating that same function from 0 to 8, and that value is 12, we could use those to find the value of the function, the definite integral of that from 8 to 10. So here's what I could do. I could say if I start at 0, the integration from 0 to 8 of f of x plus the integration from 8 to 10 of f of x would have to be equal to the integration from 0 to 10 of f of x. If I start at 0 and go to 8, pick up at 8 and go to 10, that has to be equal to 0 to 10. Okay, so let's plug in what we know. We know this first piece up here, 0 to 8 is 12, right? This is the piece that we're trying to find. And then we were given this last piece as well. We know from 0 to 10 is 17. So I basically could say 12 plus what is equal to 17. So what does this definite integral have to be? 5. So the integration of the function from 8 to 10 would be 5. All right, then over on 333, they give me some comparison properties. All right, remember yesterday we saw that if your function is above the x-axis, you get a positive area under the curve. But if your function is below the x-axis, you get a negative area for that, right? So this says if your entire function is greater than or equal to 0 for all the values in your interval, then the definite integral would have to be greater than or equal to 0. All right, here's the idea. Let's start with greater than first. If my entire function lies above the x-axis, then when I find the area under that curve, it's going to have to be a positive value, right? Or if I look at the equal to part, if my entire function was equal to 0, so I literally was laying on the x-axis, then the area under that curve would just be equal to 0, but it's still not going to be negative, right? So if your entire function is either on or above the x-axis, then you are going to get either 0 or a positive value for your definite integral. You're not going to come up with a negative. All right, look at the next one. The next one says, if f of x is greater than or equal to g of x for all values in your interval, then the integration of f of x will have to be greater than or equal to the integration of g of x. All right, here's what they're talking about. If f of x is greater than or equal to g of x, okay, so down here, every value in the entire interval for f of x is higher than every value inside the interval for g of x, right? So f of x is above g of x. Then the integration of f of x is just the area under its curve, right? Doesn't the red area have to be bigger than the green area? So that's all this is saying. The area under the curve of f of x would have to be larger than or equal to the area under the curve for g of x. All right, look at the next one. The next one assumes that little m and big M are constants, okay? So if it says, if little m is less than or equal to f of x is less than or equal to big M for all values in the interval. So look at the drawing down here. We've got little m that's a constant, and it's less than or equal to another function, and that function is less than or equal to another constant, capital M, okay? So if that's true, then little m times b minus a. Now, let's stop there for just a second. Remember, we already got a formula today for evaluating the definite integral of a constant? It was just that constant times b minus a, right? So this would be the definite integration, or the area under the curve for that constant. So basically, we're saying the area under this curve would have to be less than or equal to the area under this curve, and that would have to be less than or equal to the area under this curve. Because again, the area under the curve for capital M would be the formula we got for its definite integral a little bit ago, that constant capital M times b minus a.